there's been enormous progress in biology, but somehow if you look at it from the physics point of view, there are a number of things that physics could help with. For example, in regard to the origin of life, in regard to how to emulate evolution in a laboratory in a way that's unaided by the lab itself, obviously. So to ignite something like what happened in the biosphere on Earth, but in a lab. So I think in this context, we really haven't used the power of physics yet fully.
When Heisenberg came up with the first theory of quantum mechanics, first proper theory, it did seem very, very peculiar. It did seem to be challenging all sorts of things, and obviously it does require us to shift some of the ways we think about the world, but dismissing it as weirdness seemed to be not just missing the point, but actually missing what's so striking and even so kind of beautiful, really, about the theory. Okay, so Chiara, very nice to be talking to you.
Yeah, likewise.
Yeah,
It's been a
I
lot.
mean, thank you for agreeing to do this. It's great
Yes,
fun.
thank you. Um, I think maybe a nice place to start is what you said, because I mean, quantum mechanics is always a good topic to start a conversation. I think it's one of
Especially
those.
this year, right?
Yeah, indeed. I think so. So I think it's yeah, it's one of those years where you hear a lot about quantum theory and all sorts of statements about how weird it is and so on. And I think I know that. I guess like you, um, I don't quite agree with that in the sense that I think that it's just as weird as any other theory of physics that physics teaches us how to think in ways that are counterintuitive, and yes, it does look weird. I think lots of things in Newtonian mechanics look very weird, like accelerations and other things. But after all, yeah, I think um, I really like if we could take this year as a sort of starting point for changing a bit the narrative about the theory and making it more into it's a really beautiful or a really interesting, really deep theory rather than it's incomprehensible and we can give up on understanding reality.
Yeah, yeah.
I don't know what you think about
Yeah.
that.
Well, I mean, actually, I've got it here. This book that I
I know. I think I
several
really
years
like that.
ago. I didn't have it already, but it was just happened to be there. But the reason I called it Beyond Weird, so this is my attempt to sort of talk about what quantum mechanics means, and the reason I called it this is precisely that it it seemed to me that particularly in the kind of popular science media, but I think actually more generally, even amongst scientists, amongst physicists,
Yes.
there was this tendency to distance ourselves from quantum theory by exactly doing that, by saying, well, it's all very weird, things are in many places at once, and it's all a bit sort of hazy.
Yeah.
And it seemed to me that that was the wrong story to be telling, that we no longer need to tell that story. I mean, obviously, 100 years ago, when
It was.
Heisenberg came up with the first theory of quantum mechanics, first proper theory, it did seem very, very peculiar. It did seem to be challenging all sorts of things, and obviously it does require us to shift some of the ways we think about the world, but dismissing it as weirdness seemed to be not just missing the point, but actually missing what's so striking and even so kind of beautiful, really, about the theory. So this was an attempt to move beyond that and to, I guess, I was very mindful of, I think it was John Wheeler, the physicist, the Princeton physicist I quoted in this book, as sort of saying he had a sense that if one day we could get, well, that we will one day get to a point where we know what story to tell about quantum mechanics. We can tell it not with equations but in words,
Yes.
and it'll be, we'll suddenly think, oh, of course, that's what it was, trying to tell us all along. And I don't think we're here. I mean, I'd love to, but what I want to hear from you is how close you think we are to that. But I don't think we're there yet. But I don't think that I think we have better stories to tell than we did even 20 or 30 years ago, let alone 100 years ago. What do you think?
Yeah, I agree with that. I think there was this change of lexicon or termin. I mean, I think with quantum information theory, there was kind of a whole set of new conceptual explanatory tools that came up add, additionally to the various applications that are interesting. And I think that has improved a lot the way we think about even a quantum superposition or entanglement, for example. So this initial confusion about what it meant was clarified by first the work of John Bell, and then the way in which various experiments sort of prove that quantum theory violates those inequalities, and then what that really means about reality. And I think even if you disagree on the interpretation of quantum theory, even in each of the various sub branches of various interpretations, I think the language has become clearer, I would say. And the way I see this is that quantum information theory has contributed a lot to that. And I'm very happy that I sort of entered quantum theory and understanding it better through that angle, because that's what I started studying I think my PhD was kind of the first time I started looking into that. And then I really liked it because it clarified lots of things. And it made me uh, interested in the fact that when this is taught in undergraduate courses, it's really based still on this often based, maybe not so much nowadays, but it's often based on the old terminology that was, the same kind of terminology that was used by the founding fathers of quantum theory. And it's a shame that this hasn't been updated more rapidly, considering that while we do research in quantum theory, we actually do use a different approach to understanding measurements and other things. And I think this would help maybe this sort of displacing this misplaced, moving away this sort of weirdness take on the theory. If you train the new generations of scientists or people who think about physics in this new way, I think it would help a lot. It's happening, but I think it's a bit slow. And I wonder why is that? What's the reason for that?
I guess change is generally slow in science, isn't it? I mean, I find this in biology. We're talking about biology as though it's the 19s, and maybe we'll get onto this later on, as though it's 1970s rather than rather than 50 years after that. And yeah, I think that's probably to a degree that's what's happening in physics as well. But I do think, I mean, I totally agree that the discourse around quantum physics in terms of information, to me, it really helped me to be able to
Yeah,
make sense of this. That it's because, in a sense, that's in a sense, it's easy to say this in retrospect. It's what it's always been about, because right from the beginning, what was unusual, I think possibly unique about quantum theory, is that it seemed to be a theory about, and this is what Heisenberg himself said, about what we can know rather than what is in some kind of ontological way what is out there. And it was really explicitly about that when Max Born realized that they had suggested really that the Schrodinger equation wasn't an equation about where things were moving and what particles were doing. It was a kind of machinery for allowing us to make predictions about what we would see if we did an experiment. That was really I think that's the kind of, for me, that's the actual shocking thing about quantum theory, that it doesn't, as far as I can see, obviously pronounce on what is actually down there, if you like, that we're trying to look at. What it pronounces on, what its machinery, what its mathematical machinery gives us, is a way of making predictions about measurements. And so it's kind of the theory is pointing upwards towards us and our experience of the world rather than down towards the way things really are in some, absolute sense. And the language of information gets at that because, it now seems to be possible to reformulate quantum mechanics as a theory about how information, if you like, gets out of a quantum thing like an atom, gets out into the world where we can see it and measure it. Does that? I mean, it seems to me that that's a lot of what you've been doing with David Deutsch with constructor theory. That it's really looking at that
y-
aspect of the world.
yeah. I think maybe the thing that's really striking, as you said, is this fact that it quantum theory sort of tells us that there are all of these different properties of a quantum system. So they do have a role in the theory and in the mathematical machinery, as you say. In fact, you can even write the equation of motions in the Heisenberg way, and then you will find mathematically all the position, velocity, and there's other quantities that appear in the classical version of these equations. It's just that they don't have the same meaning
Mm,
because, as you say, we can't see them all at the same time.
mm,
And how so in a way, you can ask different questions to the system, and these questions, what's your velocity, what's your position, etc., are not all compatible, and the way in which they sort of these questions map into each other is the way in which quantum theory works. So so in a sense, it's as if there were lots of different stories that you can tell about the system, and they're all consistent with each other, but you can only follow one story at a time with observations, and that's Heisenberg's uncertainty principle. And yeah, I think that's what made people really confused at the start when they discovered the equations. It wasn't this idea made some people didn't like it, um, but I guess in a way when you start questioning the what is the ontology that's behind this sort of narrative, I think you can answer the question, and it's all to do with how these various different stories kind of fit into each other in a way, and that's what the Schrödinger equation or Heisenberg's equation of motions are about. Um, and the powerful thing about information theory is that it allows you to talk about this stuff without worrying about the details of the physical systems. So you forget about all the irrelevant details to do with, is it a photon, is it a quantum spin, or a phonon, or something else. And you suddenly have just a qubit or a set of qubits. And with those, you can simulate any of these other systems in the fundamental sense. So in, capturing all of these elements about what kind of information you can access and what you cannot with given interactions. And so this work I've done with David was trying to extract this um, abstract information theoretic essence out of the quantum structure, emancipating it in a way from the formal and physical details that you happen to have in quantum theory specifically.
yeah.
It's a bit like looking at a hidden symmetry, if you like.
Mm,
And I think that's powerful. It's nice because it gives you a way to, especially to understand things like measurement and other processes, which are all the same if you look at them in this information theoretic light. And it's true. This true in other theories too. It's just in quantum theory, as you say, it's fundamental to the theory. Whereas in classical physics, we didn't have to think like that, and it didn't matter because all the properties can be measured simultaneously by the same measuring device, and there's no such thing as a thing that appears in an equation and then you can't measure it directly.
yeah. Yeah.
Um, Although, okay, I mean, that happens in electromagnetism with vector potentials and things, but that's kind of a technicality. But let's say, broadly speaking, um, that's the case. Yeah, it's true.
Yeah, yeah. I mean, I think that point about you having to, the observer, if you like, having to choose which narrative you want to follow, which story you want to tell, and recognizing that you're then giving up on being able to say anything about the other potential stories that you could tell. That, I think, is where a lot of the confusion comes from, because it feels, I mean, what it means is that we can formulate questions about quantum systems that seem perfectly reasonable questions, but
Yeah.
that the universe can't give us answers to. It
Yes.
doesn't have the information, if you like, to answer all of those questions simultaneously. And I think that's the thing that's really hard to intuit. But once you, or if you, accept that that's the case, everything looks less weird suddenly. You just, see that that's just the structure of how it works. And I think the what you've said about the kind of almost the substrate independence of the information point of view. You're thinking about information without thinking, is it a spin, is it a photon, and so on. It's it feels to me as though that point of view has been virtually experimentally validated now. The fact that we can make quantum computers that, not only work, that actually, demonstrate that these are real things, that entanglement is real, superposition is real because the quantum computers work, but also that you can make them out of trapped ions, you can make them out of neutral atoms, you can make them out of photons, you can make them out of little rings of superconducting material, and they're doing the same thing. They're literally doing the same quantum operations. And that's really striking, that we have that tangible evidence that this is a productive way to look at things.
Yes, it's I like it too because often I guess at least at the start of the field there was an understanding of the quantum information theory. There wasn't an impression that this would be like maybe a theoretical curiosity or something that could be at best some reframing of things that are already known. Um, and okay, yeah, maybe you could get some conceptual insight into things, but there was some sort of critical voice saying, this is not that fundamental even. Um, and yet, not only did this, all of this set of things that give us access to deeper conceptual insight make us understand better quantum theory, but we also had this almost immediate or very quick effect on the technological development, which is rare to see because usually you get theoretical advances and then it takes quite a few years before there is an interest in applying those theoretical tools in the technological realm. But in this case, it was almost like a few decades later, there were algorithms being proposed, and then from algorithms to quantum cryptography things, and then from then to an actual implementation of these systems, as you said, in various physical supports, which which sounds very exciting. I thought it was very nice to see. I wasn't quite. I think I came in at the end of this revolution, but I think it must have been very interesting to be there at the start, right? So I've talked to various people who sort of power this thing, and I guess it's an interesting lesson from the general point of view that there are these very theoretical ideas which can then have an unexpected impact on the technological side, and it's not always foreseeable when this will happen and how fast it will be, and so on.
Yeah.
So
Oh God, I think that's been so clear from the what's happened to quantum information technologies, and particularly
yeah,
quantum computing. As it happens, I've just written a big piece about the state of the quantum computer industry, which it is now an industry. And in doing that, I came across a quote from David Deutsch from 2004, where he said, "I'll be amazed if." A quantum computer exists that could do anything useful within the next 10 years, 20 years, probably my lifetime. But I've been amazed before. And here we are. I mean, they're not at the level of being able to solve useful problems that you couldn't do with a classical supercomputer yet, but they're clearly they're real devices, they're being sold, they're commercially available, and they're on the threshold of being able to do things, at least for science, that classical computers can't do.
yeah,
And a bunch of people are pretty confident now that by the end of this decade we're going to have quantum computers that are solving practically important problems, maybe figuring out what the next sort of solar cell material needs to be, or helping drug discovery or whatever. And that's it's astonished me how quickly that's happened, and I was kind of relieved to find that it probably would have astonished David to have seen that as well. Um, but it's an idea that goes back. I mean, he first had this idea, I guess it
yeah.
was 1985, wasn't it? That he came up with it, and then Richard Feynman suggested the whole notion of simulating materials, quantum things, using quantum mechanics in 1982 or thereabouts. So it took a long time to get to the stage where people, I suppose it was only really at the turn of the millennium that people were really starting to make to realize these sort of quantum algorithms in things that
Yes.
actually did stuff. But the speed at which it developed, thereafter, and particularly in the last 10 years or so,
Yeah, it was impressive.
yeah, I mean, has that surprised you? Because you've certainly been in it long enough to have seen that development.
Yeah, I think it was quite fast in a way, and as you said, and I think the thing that really amazed me, because I come from this very theoretical, so I'm kind of interested in in the fundamental aspects of the theory, right? And it's very nice to have a case where it's almost immediate that these very fundamental ideas that are important for fundamental research in physics, mm, all of the information theory based ideas that are kind of related to entanglement theory and measurement theory and so on, are all relevant for these things. And these ideas are almost informing directly the applications, and it's a beautiful example to quote even to the public, right? To show that it's often the case that these fundamental things that we look into in physics are very far reaching, and they can dramatically change various things at the level of technology and then society and so on. This has happened, of course, in the past, but I guess on a longer time scale. And in this case, I can see it's very compressed, as you said, in few decades, and it's quite nice to see that. It's exciting.
Well,
uh,
yeah, I mean, what strikes me about that too is that I think it challenges the traditional idea that that science always goes from the sort of fundamentals, the basics, to techno, and then feeds into technology, and then sort of technology does its own thing. Here, it feels to me as though it's always been two-way, that actually the technical advances, what you need in order to be able to make a quantum computer work in terms of things like how to correct the errors in your quantum bits, the thinking that goes into that feeds back into thinking about quantum fundamentals.
yes,
And
yes,
that's what's
absolutely.
so striking to me.
Yeah, yeah, I think it's beautiful to see. And yeah, and on the other hand, it also says that those people who were thinking about the fundamental ideas were not really necessarily interested in the immediate applications, but then those applications did come. And so this, I guess, this helps when you're thinking of, um, you know, what will happen next, because I guess at some point we'll have a new theory after quantum theory, and presumably will support quantum computation, but more than that. And then we need to prepare for that. So this kind of, I guess that's one of the themes of my research, or one of my interests, um, which is how do you how do you see, in the absence of experimental discrepancies between what we currently know about the universe, so the quantum theory, general relativity, they seem to be all very well confirmed. So, in the absence of things that, at least in small laboratories, can falsify these theories, what can you use? What kind of tools can you use in order to imagine which bits of these theories will stay when we think of a new theory, and which bits will have to go? And that's a very interesting question. I think it's been thought about by many people, but I guess it's nice to imagine maybe different tools to think about that. And I, um, I'm really curious. I'd like to be surprised about about the new theory, but I'm kind of guessing that many of these beautiful properties of quantum theory will stay, but there'll be more. And then this more will be as weird and, superficially weird as quantum theory was to the people who found it. But it will maybe power new quantum computation, or quantum-like computation, or post-quantum computation effects. And it would be nice to have the tools to understand that. So I think that's kind of I guess maybe that's what's happening at the fundamental level in the field. So, because now, as you said, this has become almost like an industry, right? Quantum technologies, they are really well established things. And then you'd like to think what's next.
Mm, yeah, yeah. Okay, I'd be interested to probe that a little bit more, to of what you're thinking will stay and might go. I mean, I've been just recently also talking to some people about quantum gravity from the point of view of not what is, where are we going to find a theory of quantum gravity, because it feels like that is totally up for grabs at the moment and we don't know where to start, but simply the question, how sure are we that gravity is going to be a quantized force? It's really interesting because, some people said, well, of course we're sure, it's because the world has to make sense. What else can it be? Gravity has to be quantum. And others said, no, not necessarily.
Yeah.
I wouldn't take for granted. I mean, certainly, we have no empirical evidence of that, but also there are ways of resolving the tension that you get in general relativity, where you've got on the one hand the sort of continuous curvature of space-time, and on the other side of the equation you've got mass, which is quantized. There are ways of resolving that don't require the curvature to be quantized. So it's not a given by any means. So I've been talking to people about experiments that can be done that are tractable, that aren't going to test string theory because we're way off that, but that can, in principle, test whether gravity is quantum or not. And that's really interesting that you can do that in the lab. And it seems like the way to do that is, again, coming back to quantum information to see. In particular, one idea is that you'll be able to, if we can entangle two quantum objects purely interacting by gravity, they're far enough apart that there isn't any significant electromagnetic interaction. If we can entangle them that way, that shows gravity is quantum. I mean, do you have a do you have a feeling for
Yeah.
what we're going to find?
Oh, yeah, yeah. I think I'm very excited about the experiment because we, well, I think Vlatko, Vedro, and I kind of suggested one version of that sort of experimental scheme, and we got very surprised that you could actually, as you say, do this in a laboratory that is at low energies without the massive accelerators that you have in CERN and places like that. And the other surprising thing was that, and I think this was also found by Sugato Bose and his team. I think they also kind of worked on this experiment. Was that, as you said, the kind of tools that you need in order to predict this effect are mostly information theoretic. In fact, you can base all of this on some constructor theory of information type reasoning, and so the insight is really that you can do some tests which is very simple, and the simplicity somehow has a cost, as you were saying, that you can't really pin down which model of quantum gravity may generate this entanglement if you were to detect it. But if you were to detect entanglement, then yeah, you could conclude that gravity has to have this feature of being quantum, or at least non-classical. It can be described by classical theory like GAR or some of these other semi-classical models. Um, my intuition is that we will be able to see entanglement. So I'm kind of in that camp. So I am not a skeptic. I am very happy to think that gravity is quantum, and that I was very taken by some of these early arguments by Bryce DeWitt, who is this very I mean, of course, he was I think David's mentor, but he has a very mathematical physics sort of take on things. So his books are really, really hard to decipher. So, sometimes with David we say, all the answers to quantum gravity problems are in there. It's just we can't decipher it because it's mathematically really challenging. I think he was a very hardcore mathematical physicist. Um, but some of the things that I could decipher had to do with his arguments, which are very interesting, where he wanted to say that if you've got one sector of the universe which is quantum, and then this sector somehow interacts with a reasonable interaction with anything else, then this anything else has also to have quantum features. So it's a bit like sort of infectious. Probably that's not a good thing to say now after COVID, but it's not something that spreads as like a sort of infectious disease, the quantumness. Once you have it somewhere and then there's an interaction with the rest, then the rest also has to be quantized. And I think these arguments have been questioned and challenged, and Vlatko and I at some point we tried to find a better version of it that didn't have some of the strong assumptions that we'd had. But I have an intuition which says that these things should be true, that this is kind of a reasonable statement to make, because it's as if like you had, again, from this information theoretic point of view, you got something that has this very, this larger processing power in terms of information, which is quantum system. And then you make it interact with something that um, is, mm, is somehow less powerful. Um, Now, if you maintain that this interaction has to have some of these features like um, conserving, in some sense, information, so maintaining the number of degrees of freedom involved and so on, then this uh, higher processing power has to somehow percolate in this other classical area. And so the classical area, in fact, is not classical, but it's got some quantum features. And it's a nice argument, and it seems intuitively right to me. So I'm expecting that in the experiments, when someone will perform them, we will see entanglement. And that will be interesting because, I mean, at least as you said, it will validate the quantum gravity programs that have been maybe, you know, there's been a lot of progress there, but somehow it's been difficult to reconcile them with experimental evidence because all the predictions seemed very, very far from anything we could do. And now it seems like we at least can validate the whole program, as opposed to having just a classical theory.
Yeah. And I guess like we say, that isn't something we can take for granted, because even someone like Roger Penrose has. I mean, some years ago, Roger said to me,
Yeah.
"I think quantum mechanics is going to break first before general relativity." So he has this idea that somehow gravity sort of enforces classicality. So that there's something, at least, that that's an idea, at least, that can be put to the test with an experiment like.
Yes, and I think the powerful argument is there is that perhaps our intuition is more with the classical realm, isn't it? Because we are immersed in a classical surrounding, and then we have the intuition that somehow that should be the fundamental aspect and not the other stuff that quantum theory tells us. But again, um, it's a bit like with relativity, that there are lots of things that seem counterintuitive, but then they're true. And so I think it's, yeah, I'd guess, I'd bet probably the opposite way than, compared to Penrose
Uh-huh.
in regard to what should prevail. But it's interesting that this hasn't been settled in such a long time. It's very interesting, it's a century, right? That more or less that
Yeah.
these theories have been around, and we haven't been able to figure that one out, right? So
Yeah.
it's interesting.
Yeah.
Um, and I think this is related to the confusion. So it seems to me that because somehow there have been these, I would say maybe hang-ups about quantum theory, what you were saying initially, that there has, took a long time to digest even what quantum theory meant, um, physically speaking, and then, with information theoretic structure being so different from classical physics, etc., that perhaps because people are so they are so much in disagreement about what it tells us about reality, it ends up being very difficult to imagine what the successor should be like, because some people are thinking in one direction and other people are thinking in a completely opposite direction. Like, as you said, Penrose is thinking in a classical fashion, and then other people are thinking, no, it should be quantum, and it should be like this and that. And so the efforts haven't been concerted. They've been sort of going to really different directions. And I think it's related to the fact that quantum theory has been so hard to be, absorbed by, even by the scientific community itself. Um, Maybe that's slowing us down in some way.
Yeah, well, I mean, it's often sort of commented on that, 100 years later, we haven't actually narrowed down the question of what quantum theory is telling us about reality. And if anything, we've got more interpretations than ever before, and they seem to be proliferating. So yeah, it's, that testifies to how difficult it is to really, figure out what the theory is telling us about what is out there. Um, I wondered. One other thing I'd be interested to explore with you, Chiara, is and something that I'm very interested in looking into just at the moment is how quantum theory is impacting the way we think about thermodynamics. That's another big area that's sort of come about very recently,
Yes.
and what seems to me to be so striking about this is the existence of these quantum correlations between objects that can't be accounted for classically. Means thermodynamics, the theory of heat, really, of how heat gets around, it was a classical theory originally. The existence of these quantum correlations, this sort of these sort of if you like, these extra degrees of freedom that it almost provides, means that it seems possible to do things thermodynamically with quantum systems that we can't do with classical systems, getting engines to work more efficiently, getting even batteries to charge more efficiently. And there are ideas about whether we can use those differences to actually probe for quantumness in a system, by the differences in the heat exchange that you might see, for example. So I'm curious about what the way you've been thinking about quantum thermodynamics.
Yeah, I think it's a very interesting field, and in a sense, I like quantum biology. I was initially very excited about it because I thought that, simply because I was thinking about it from the point of view of the quantum information revolution. So I thought, oh, great, now we're gonna have a similar pattern of thinking in thermodynamics, quantum thermodynamics, and quantum biology. Um, and at the moment, I think there are some kind of very interesting ideas out there. However, I'm a bit worried about the fact that, um, broadly speaking, I think I agree with you that there should be some way of tapping into the quantum coherence of systems in order to make some engines more efficient, and then take advantage of that in thermodynamic cycles and so on. And there have been suggestions of this kind. Some people have performed some experiments, like proof of principle. Um, but I have two big somehow worries about that. So the first worry is that most of these things, the results that being proposed, are mostly reproposing tools that we already have in quantum information theory in a different context.
Mhm.
But it's very difficult to make a very convincing statement, unlike with quantum computers, that there is a truly quantum advantage when you find, for example, that a quantum engine is working in a more efficient way than its decoherent quantum counterpart. And that's because, you could always find a skeptic that says, yeah, okay, this one seems to be, in this case, it seems like, yeah, it's true. But then, I could find a better classical engine, just a more efficient one on the classical side that could outperform the particular quantum engine you're talking about. And the reason why it's impossible to counteract that claim very convincingly is that we don't have, unlike in the quantum information theory case, there isn't a theory of a universal quantum computer that's underlying the equivalent of the universal quantum computer in the case of quantum thermodynamics. Why am I saying this? Because I have an interest in these, um, at least broad interest in these machines that are called constructors, which are supposed to be generalizations of computers. And there is a way of talking about an equivalent of a universal computer in the case of a heat engine. You just have to think of a programmable machine that has a number of functionalities in it that go beyond simply the computational power, and can underlie various thermodynamic tasks. But we don't have a theory of that machine, so it's difficult. So in the case of the quantum information theory, the reason why you could argue for quantum advantage in terms of algorithms and so on is that you could rely on this very strong theoretical sort of basis, which was given by the quantum theory machine idea, and then the circuit model with the gates that is equivalent to the sort of Turing machine model. And then on the base of that, you can make then some comparisons between the quantum Turing machine, the universal quantum Turing machine, and the universal classical Turing machine. But in the case of thermodynamics, is not so easy because we don't have a theory like that. And so there's a kind of, I think, at the foundations of the theory, that's one worry I have, that there is a gap that one should fill in some way. And I don't know how to fill it, but I think it's something that maybe would be nice to think about, theoretically speaking. And the second worry I have is that um, I so I think the strength of thermodynamics, at least in the in the way that it powered the Industrial Revolution, um, was that it had this nice substrate independence. So it was when the first few ideas about thermodynamics with energy, entropy, and thermodynamic cycles that people like Kelvin and Clausius proposed, and so on, and formulations of the second law, they were formulated in a way that was at a higher level compared to, say, the dynamical laws that were known at the time.
Mhm.
So they were not piggybacking on, say, I don't know, Hamilton's equations and things. Um, Only at some other point it was proven that you can, with statistical mechanics, recover, for example, the second law from microscopic dynamics, which is a great result in its own right. But what I'm thinking that if you think of applications and ways of really impacting thermal engines and so on, it's very nice to have a formulation of thermodynamics that doesn't rely on the microscopic dynamics, much in the spirit of the original thermodynamic statements, like the first law, the second law, and so on. And I think the quantum thermodynamics at present doesn't have that, because most of the laws, the various ways in which the second law has been formulated in quantum thermodynamics and the extensions compared to the classical second law, they're all just basically using the Schrödinger equation or quantum theory's equations. And I think it hasn't been emancipated, all of this set of results from the from simply from the dynamical laws of quantum theory. And I think I see this as if you think of it from the thermodynamic point of view, this is something that should be fixed, because I think once you did that, you would be able to. If you did that, you would be able then to have a more robust structure and a more powerful way of understanding the implications of these second laws. Um, and okay, I've done some work in that direction, but I think, broadly speaking, these are my two sort of open questions for the field. And I'm hoping that someone will answer those questions, or maybe I will with, some of my work. But it's an interesting open question, I guess, that might be nice to find an answer to.
So, I mean, it sounds to me as though what one aspect of what you're saying then is that you don't feel quantum thermodynamics has an emergent aspect to it in the way classical thermodynamics
Yeah.
has, in that you, as you say, we can use and do use classical thermodynamics without worrying what the molecules are doing. It's not that
Yes.
level. Yeah. And I mean, that's a quite a very sort of general aspect that it seems to me your work with constructors is trying to get at anyway, is to sort
Yes.
of understand how we get to complex systems at a higher level of complexity without having to worry about the details of the microscopic. Is that?
Yeah, I think this is an interesting. This is definitely something that interests me, broadly speaking, and I think it's maybe something that's currently um, perhaps overlooked by some of these various approaches that you mentioned, within quantum thermodynamics for sure, and maybe more broadly speaking. And the reason why I like this kind of question is that somehow the quantum information theory story has demonstrated that you can have laws, just like the thermodynamic story. You can have laws that are fundamental, um, some of which aren't even exact, so they don't need to use maybe probabilistic statements or coarse graining statements and so on. But they apply at all scales, so they are not just true of microscopic particles, but they apply at a higher level as well. So laws about bits, for example, it doesn't matter how large or small a bit is. Um, all bits obey the laws of information theory. Likewise, qubits. It doesn't matter how many sub parts a qubit has. If you see a qubit in a dipole within a macroscopic molecule in a biosystem, that will still obey the same qubit laws as electronic spin in some atom. Um, and I think there are more of these laws around, and it would be really important for us to find them out, because they could supplement or I would say nicely help us with understanding the microscopic laws as well. So it's not that they would be in contradiction, it's more like, as in the case of the second law, they would help us maybe find new laws of dynamics that may supersede the ones we have. And they are also interesting. They're also useful when, for example, you don't want to use the dynamics to calculate things. This is even just a question of being lazy
Mhm.
or incapable of doing, of solving an equation that's intractable. But you can still use the principles to make conclusions that are very strong and powerful. And it seems to me recently, this was used in the past, but it seems to me maybe recently we've forgotten the power of principles. And it's a shame because I think they could do a lot for us, both the new ones and the ones we already know about. Um, it's always nice when you could get these problems in school when you have to figure out some things to do with energy and so on. And it's always cool that you can reach the solution by solving Newton's equations, but then you can use the conservation of energy and there's one line proof to show what you want to show. Um, and I'm always hoping for that kind of use of principles that, if you like, is not even about how fundamental they are. I think they are, but even if you don't believe that, they're still quite nice as shortcuts to get to some interesting prediction. And it seems to me, because we don't have at the moment a very good intuition about what the future theory might be after quantum theory and general relativity, I think these principles might be useful in that area as well as in the macro world, as you were saying. So maybe understanding bits of how life works, which I know you're interested in, and thermodynamics too, how to augment it and how to make it more useful to us. Maybe a second industrial revolution, like where we discover more efficient things that are based on quantum processes.
Okay, so I'm very interested in this. It sounds as though, so am I right in thinking you're saying you suspect there may yet be laws that we could possibly consider fundamental laws, even if they're not operating at the smaller scales we have, laws of nature that have yet to be discovered, that we haven't necessarily yet found out. It's not a question of finding out the fundamental sort of law that's going to unify quantum gravity, the quantum mechanics and gravity, but that there are higher level laws, maybe macroscopic laws, that we have not yet found out. Is that your sense?
Yes, I think so. Just to get it right, I'm not suggesting that these laws would contradict the dynamical laws.
Sure. Yeah.
I think
Yeah.
I'm completely happy with these principles
Yeah.
being compatible with what we know, obviously, about dynamics. But I think, yeah, we are. There are lots of areas of the natural realm that we haven't looked at from the physics point of view. For example, biology is. There's been enormous progress in biology, but somehow, if you look at it from the physics point of view, there are a number of things that physics could help with. For example, in regard to the origin of life, in regard to how to emulate evolution in a laboratory, in a way that's unaided from by the lab itself, obviously. So to ignite something like what happened in the biosphere on Earth, but in a in a lab without the help of with the lab itself, because that's the whole point of why natural selection is striking, that it happened without anyone doing anything about it. um So I think in this context we really haven't used the power of physics yet fully, or in fact even started. Okay, then there's also the physics of the mind. That's something that we haven't uh, tackled from the. I think some big thinkers have been thinking about these things broadly, but it's very difficult to make statements that are not just descriptive.
Yeah. Yeah.
And physics is good at making these non-descriptive, explanatory, predictive statements, and we don't have those statements. We struggle to formulate, and I think that's because we lack understanding of the fundamental physics laws that rule these mechanisms that power both life and thinking.
Right.
And I think there could be some space for physics there. So I do regard these things as part of physics to some degree. And I think we should, we physicists should kind of look into those things more. I would be
I mean,
very proud.
of course, what some biologists at least will say is that it's evolution takes care of all of that. And specifically, Darwinian evolution takes care of all of that, that we can understand whatever we see in an evolutionary context. There is, if you like, a story we can tell about how it got to be the way it is. And in general, it got to be that way because there was some adaptive benefit to it. But one of the things that's often said about that way of thinking is it's not predictive. Evolution, Darwinian evolution is not a predictive theory. It doesn't tell us anything about what's going to arise in the future. Are you thinking that physics might be able to make it more of a predictive science?
Yeah, so I'm a great fan of Darwinian evolution. Actually, I really like the theory. I think it's spectacular and it's very interesting as a machinery of the kind of way in which it explains things is very counterintuitive and cool. Um, and I do think in some sense it is predictive because it tells us things like that if we find a different kind of form of life on a different planet, it will still have to have some basic structures that are the same as ours. Never mind what chemistry it will use, but it has to have these things like replicators and then something that's the phenotype around it, and then um, error correction if it's beyond a certain stage of a certain level of complexity and so on. So in that sense, it is predictive, but it's not predictive to the degree that it can tell us which species will arise at some point in the future. Um, and the kind of prediction I have in mind is perhaps a bit different from this latter thing I said. Um, it's more about um, questions of the kind, once life is started somewhere, what is the what can you expect about its trajectory? So once you exceed, if you want to be quantitative, once you exceed a certain level of complexity quantified by some measure that's suitable, and then we can discuss what measure to use. Um, Considering the environment the way it is, and considering various other aspects of where this life is, what are the what's how likely it is that it will survive a certain number of years later, at t equal whatever. These questions are somehow difficult to answer with the machinery we have at the moment, but they are important, they are interesting, and they're based on us understanding what is it the stuff that makes life robust, resilient, that has this property of being permanent in a world that tends to sort of being impermanent. Um, as I said, all of these things that we are saying are very descriptive. We can still say what it is. It's obvious that we have DNA and there are other sort of information that's sort of used in the, there are all sorts of explanations that are very convincing. But I think I'm dissatisfied with the fact that we can't answer some of these questions. And it would be nice if there were a principle behind it. I don't know what kind of principle it could be, but maybe akin to the second law or something like that. And maybe biology will come. At some point, biology will use some of the tools of of physics and borrow them. I'm very happy if biology ends up, deciding to do that. But what I'm saying is that we should answer ask these questions. I think they're important questions. They are not just things that I'm not very happy with dismissing problems simply because they belong to some, they are above a certain scale. I think they're all valid problems and they're interesting. Um, and physics should take them seriously.
Yeah. Well, I mean, I imagine you will have come across the recent work by Bob Hazen and Mike Wong and people at Carnegie Institute, who are proposing. Does this ring any bells?
No, I haven't.
Ah, okay. They are. There's a whole bunch of co-workers they have, planetary scientists, philosophers, who are suggesting that there is such a law that can, to some extent, predict the trajectory of biological
Yes.
evolution, and not just of biological evolution. That in essence, it suggests that there will be increasing complexity in any system, which isn't something that's predicted by evolution. In fact, it's a
Oh
big
no.
point of debate whether, if life developed on another planet, would it ever get beyond bacteria or something like bacteria,
Yes.
and was it a fluke here, or is that the general trajectory life will have? Clearly that is what happened here, that although obviously there's a lot of bacteria still around, there are life forms that are, I think, unquestionably more complex now than they were, 1 billion years ago and 2 billion years ago. Is that a general principle? And if so, how does that arise? And they have the idea that they're talking about it in terms of a quantity they call functional information. This is an idea that Jack Shostak at Harvard came up with many years ago, which is to do with the functions that objects have, which is itself really a concept that it's hard to imagine outside of the biological context, although these folks suggest there is a way of talking about that. But it's to do with whether you can find other configurations of the same components that do the same job.
Yeah.
And that defined in that way, they argue that there seems to be this push towards higher functional information, greater complexity in any system. So it's certainly an issue that's being talked about, whether there is a law like this, because again, the second law of thermodynamics doesn't give us anything like this. In fact,
No.
in some ways, it seems to
In
give us
fact,
the
no.
opposite.
It says the opposite
Yeah,
almost, right?
yeah.
It's it.
And it doesn't
Uh,
conflict with that. It doesn't, everything is happening. We believe everything is happening, while observing the second law, but it's something that goes on top of that. So no, I think you
yeah,
find it.
this is something like that. I have in mind. So I don't know this particular work, but I think it sounds interesting. And my impression is that there should be. It would be nice if we had more of these kind of proposals because that's a very rich area of problems, and these kind of results would be helpful for a number of things. And so I perhaps the problem with looking into these things is that physics has been accustomed now to reducing everything to the dynamical laws, and then it becomes difficult to maybe tackle these questions, given that you might need a combination of tools that involve both dynamics, but also other kinds of thinking along the lines of principles that are not necessarily expressible in terms of dynamics.
Yeah.
And so in that sense, I think it's yeah. I guess what I'm saying is that um, it would be nice to see more of these things and more diversity around when we tackle these issues. Much in the way that I really like some of these ways of thinking that some physicists and mathematicians had in the past. Like, one of my heroes is von Neumann. I really, I haven't managed to understand or read any, nowhere near the whole of what he wrote and did. But I think he seems to me he embodied this very beautiful thing that physics has, that because it seeks universality in its laws, then it makes you think about things that don't look obviously like they pertain to physics. It's actually part of
Mm.
physics, right? So he had the thing for biology. He wanted to understand how self reproduction works in bacteria, etc. Then he came up with this idea of constructors. But that's all part of this very general thinking that didn't think of, barriers between subjects and stuff. The, just thinking of problems, and you follow them wherever they lead you
Yeah.
to. And I think maybe we're kind of missing that in physics nowadays. There's a lot of focus on perhaps very focused and I would say, um, there's a focus on subjects and sub-subjects and
Mm.
subfields,
Yeah,
and being very
specialization.
careful about not stepping out of the
Yeah.
small field.
Yeah.
And I think maybe that's not how it should be. I think you should just look for problems and try to solve them if you can with the tools you have.
Yeah.
Um, yeah. So I guess I'm hoping I think we'll solve these problems. It's just a question of thinking about them in the proper way.
Yeah, I mean, I'm sure that there will be biologists who feel a shiver go down their spine when they hear talking like this, because there is, of course, a history of some physicists sort of stepping into biology and saying, "Look, I'm going to solve all your problems that you guys are
Yeah.
smart enough to solve." But on the other hand,
Very nice.
as you say, there are people like von Neumann or Schrödinger who came in and made really valuable contributions.
I think there's always a risk of oversimplifying problems, but then I guess that's part of how you find the truth. Sometimes you come up with very wild ideas that don't work, and then people just tell you that this doesn't work. But I think if you never ask the questions, then you will most likely never come up with the ideas.
Yeah.
So I think somehow, um, of course, with the understanding that if you don't have the expertise to address a question, you shouldn't just tackle it without having the faintest idea about what you're saying. But it's um, I think there is a value in the way physics tackles that. There is something unique about the way physics tackles questions, because it has this ambition to being universal. So the fact that you're looking for universal laws allows you to see connections between phenomena that seem very, very different in the way they manifest themselves, but actually they have this unifying explanation underneath. This is true of all sciences, but I think in physics this has maybe the most clear manifestation. And sometimes this is relevant for other fields of science. And biology seems to me, especially evolutionary biology, has a lot of potential for that. Partly also because it has also some overlap with information theory. It's again one case of understanding evolution and the way in which complexity arises is another case of a situation where you can abstract away some details of the biological functionalities and systems, and then try to look for patterns that have to do with information theory laws. Because ultimately, the things that are supporting the biosphere are these strings of information that are being copied. And the laws that apply to those things are the same as those that apply to kind of bits in computers and so on, of course, with differences. And I think this has there's a potential in that which hasn't been fully used, it seems to me. So we should
Yeah.
kind of
Well,
capitalize.
as someone who trained as a physicist many years ago, I'm obviously inclined to agree with all of that. But it always feels to me a little bit of a shame that we've come probably to associate physics with, a department of, and it says physics on the building and it says physics
We,
on the door. And so that, speaks to sort of academic specialization and turf wars and so on. Whereas I totally agree that there is a physics of all kinds of, there's physics of traffic, there's a physics of society, there is a
economics.
physics of the cell, all sorts of physics of the cell, that don't have to be something that's studied by physicists in physics departments. It's a way of
Yes.
talking about phenomena that is
Yeah,
different from looking at the specific details of how this protein interacts with that one and so on.
exactly. Exactly. Yeah, I couldn't agree more. Yeah. Um, and maybe this I don't know, this can touch maybe on the I don't know the last broad area that we can talk about today, depending on how you feel. But I thought maybe we could. It's nicely tied with perhaps with a reflection on how science is going, broadly speaking, because I I followed your work on various, in various directions, and I think I like the this mm, this look you have on how science feeds back into society, and especially also in the context of pandemics that we had. But broadly speaking, it seems to me that various aspects of how science is funded, how it's perceived by the public, how it's communicated to the public, have changed maybe the way in which actually researchers end up working. Meaning, at least I've seen this as when I was, finishing my PhD, then starting the postdoctoral research phase, and I've seen many colleagues like me. There's a very there's like a lot of collateral activity that you have to grapple with and do in addition to your research, and you're often encouraged to look into problems that seem more well, I would say either fashionable or easier to sell to funders or public or whatever, um, instead of just following the problems that you're interested in. And I think that's not a good thing. I think it's a very problematic thing, and you know, it'd be better that the whole set of incentives could be changed or modified so that people didn't feel so pressured in looking into incremental problems all the time just to publish. But I was wondering if you had a more like a different angle on this, or you had a different perspective, or some thoughts about this stuff. How do you see it from your
Well,
perspective?
I mean, fortunately, fortunately for me, I'm outside of that whole system, so I can allow my curiosity to take me wherever I like, and hopefully write a book about it or write an article about it, and that's wonderful, and that's the privileged position I'm in. But
Lucky for us too.
I'm very aware that in academia, that's very rarely possible, and I mean, that's why I'm so impressed that you seem to have managed to be able to look at problems that can go in all sorts of directions, including biology and evolution, as well as quantum physics. I think that's very unusual. Um, but this is a problem it's often kind of talked about, paid a lot of lip service. People talk about interdisciplinarity and transdisciplinarity, and blue skies research and so on. But somehow it doesn't seem to get translated into particularly what young researchers can
Yeah.
do. And some years ago, I was told, and I think it's only got worse since then, I was told by a group of younger researchers that they don't have time to think. I think that's the crucial thing, that you've just got to be producing stuff. You can't actually, even about the field, that the particular field that one is
Yes.
working in at the given time, there's no real time, proper time to sit back and think broadly about what the issues are, what's important and what isn't, what the field might benefit from that isn't there. These sorts of questions that I think in the past scientists did have the opportunity to really think about. So I definitely think the situation has got worse, not better, in terms of the constraints that young researchers have and the pressure to produce in a very the only way you can produce really in an impactful way is to do it very narrowly in a particular field
Yes.
that is going to get published, and it's well established, and so you
Exactly.
can't take risks. So I do think that there's something that needs to be really urgently needs to be thought about there. I'm afraid I don't really have any solutions other than I've heard people say maybe sort of 10% of research grant money should be put aside for things that don't you're not going to be told what not going to be asked what the applications are going to be in 5 years' time. But I don't see that happening. So I think it's very clearly a problem. Um, and I guess if it turns out to be the case that only researchers at the end of their career, when they're the sort of grand person of the field, they can sit back and speculate more wildly, and that's not the right time to be doing it anyway, I think, because your ideas are set in stone then. If that's the only way that sort of thinking can ever happen, then that's really, really problematic. But I mean, maybe you have answers to that, because, as I say, it seems to me you've been able to sidestep some of those problems.
Yeah, I think this was down to some, well, accident of the fact that I managed to find some funding that was flexible and allowed me to, to look for things that I was interested in. This is, I guess, maybe it's a positive side of things, that now you have a number of possible different sources for funding, and there are some foundations that are happy to fund research that is maybe less likely to be funded by governmental funds, precisely because it doesn't immediately recognizable. It's not immediately within some areas that are that's currently very hot or very researched into. Um, and also down to the fact that I think, well, that I think I'm doing physics because I really like thinking about it. And if I have to end up doing things that I don't like doing, then I might as well just change profession and do something more mundane and sort of stable. And so in a sense, I my stubbornness, and together with the fact that I managed to find some funds to support me, I managed to retain some sort of independence from the system so far. But it is difficult, and I think I think it's all to do with this fact that there that society maybe, and broadly speaking, governments don't maybe appreciate this link from between fundamental research that doesn't have an immediate application and benefits for society. I think this is something that hasn't been absorbed by enough by people. Even though, of course, it's under, it's obvious to anyone that, progress in medicine, because we had diagnostic machines and they come directly from quantum theory, progress, and other things. And then, biology, likewise, various fundamental breakthroughs came from understanding DNA and the structure. So those were all bits of fundamental research within biology itself, and so on. Uh, well, computers, Turing, I mean,
Yeah.
that's a very good example of some research that was done for the sake of understanding proofs and abstract mathematics, in a sense, and then they ended up providing the internet and other things. But I think maybe I don't know, it's really, there's a counterintuitive aspect of what you were saying, that it's, the money that you spend on a number of ideas that maybe 9 out of 10 will turn out to be wrong is really well spent if that one idea that's right is a good idea, is something really fundamental that shifts the boundaries of knowledge by quite a lot.
Mhm.
Um, and maybe it's good to fund some of those things rather than funding all of the ideas that seem to be quite safe bets, and then sort of they achieve things, but they don't surprise you that much. This is really difficult to explain, I think, to people who are not in science.
I think it's that phrase that's often sort of said, that if you're not failing, then you're not doing it right. I think that's maybe one of the big things
Yeah,
we have a problem with failure.
yeah.
That actually, you absolutely, if you don't have some projects that are just failing, that don't go anywhere, then then you have the wrong model, because you're not then also going to have the ones that unexpectedly produce something amazing. And it might be 1 in 10 of high risk projects that do that, but that's the only way you'll get those real breakthroughs.
Yes, I think this is also well, there's probably some fault with the feedback system as well, because when you are given a grant from a governmental agency, there isn't a lot of interest in what you've actually done, but it's more like, have you succeeded to the degree that you ticked all the boxes you said you would tick. The point is that if you just said, so it's somehow very, as you said, very embarrassing that high risk programs of research funding, they end up having, I don't know, 99.9% success rate. um, because it can be then high
Yeah,
risk. It's,
exactly. Yeah.
can it be high risk, right? And no one worries about that. I think lots of money is being given with the idea that this is really, as you said, blue sky research and so on. And it's often good research, but somehow it's not quite doing that exploratory thing that should be somewhere in the broad portfolio of things that the government can fund. Um, and and I think um, the there is some, I would say there's one aspect in the picture that makes things harder is that the way we have to communicate results currently is it's a bit like when you're in a room and everyone is shouting. In the past, maybe most of the results that are being published now would be probably put into a letter that you would send to a colleague. Maybe not all of them. Most of them would be in notebooks that you wouldn't show anyone. But I think it's you have to present them as really great results
Mm.
that have shifted the boundaries of something, and it just can't be because if you're churning out results every 3 months, it's just not possible. And it's a bit problematic that no one is moderating the way of. If you look at the titles of papers of 100 years ago, right, when you look back into these early quantum papers and the way they were communicated, they look very very matter of fact, um,
Even boring,
understated,
actually. Yeah.
even boring actually, yeah. Whereas now it's like there's so many titles that sound like we have earth-shattering results, and then well, they may be interesting results, but they are not
Yeah.
of the same caliber as those other initial ones, right?
Yeah.
And somehow this doesn't help. I guess, especially for the public, it's difficult to understand. And I think when you communicate science, I think it's also important to strike a balance between explaining things properly and getting the attention of the reader, but without trying to tell them things that are not true. And it's difficult at the moment. I think it's social media are not helping either with this. So there's a whole of there's a set of things that are conspiring towards this kind of accretion of incremental results being presented as huge results, and public being unable to actually judge whether what is what, which is which,
Yeah,
and that's
and they get disillusioned. I mean, part of the result of that way of presenting things is that you get a lot of retractions now. More retractions than
indeed.
we used to get. There are a lot of results that, yeah, that don't pan out, and that probably wouldn't have got published if if we had more time to think things through and work things through and to examine them properly. And I mean, I guess I sort of had a small hope that the pandemic might have helped in a little way to show, because we saw science playing out in real time, including all the uncertainties and the false
Yes.
leads. And, there were things that were believed at the beginning of it by the top scientists that proved not to be true in terms of
Yes.
how the virus was transmitted and, what its transmissibility was. And that's just normal science. But I think, we do kind of sell this idea that science gives you cast iron certainty the moment something is published, or even the moment something is, announced. Um, and it would be nice if that had been the case, that, we could say, well, perhaps people understand, that science works that way better now. I rather fear that the message people have got is, well, anyhow, you don't know who to believe. Maybe you don't, maybe none of them really know what they're talking about, because so many things seem to change along the way.
Yes, actually this is terrible. It's one of the worst outcome of you're right that I was also hopeful that this would initially I thought that this would really, change forever the way the public thinks about science, but it did it in the wrong direction. It and it was also um well helped again by the fact that it seems to me nowadays it's very difficult to read things in detail. When some information gets out on the internet, some bit of information, then whether it's false or not, doesn't matter. Once it's gone, it's gone. And even when you correct it and you keep saying, no, it's not true, it's so hard. It's like an irreversible process. There should be some law there, some kind of, irreversibility, because it's really impossible to remove false things that have been proven false from the wide beliefs of the public. And that's
Yeah.
part partly because the social media
Well, I think
are so.
sometimes because also it feeds into particular agendas or just particular preconceptions, that
Yes.
I mean, it's a well-established thing for all of us that if we hear something that fits our preconceptions, we're more inclined to believe it.
Yeah, it is easier to kind of make it part of your own set of beliefs and not engage with the correction once it's out. Yeah,
Yeah,
it's
and and social media now is just such an amplifier of that and such an accelerator of that process that's always been there. I think that's one of the problems we're up against. But I mean, I sort of wonder whether some of this comes back to normalizing mistakes and normalizing getting things wrong and things not working, which is something, because we'd see that in kids from the very early stages of schooling. You have to get the right answer, and
yeah,
the idea they get is there is a right answer. I just have to find it. And if I find the wrong one, then I've failed in this task, and that's bad. And that's really it feels like that's the root of the problem. That if we can somehow get young people to understand that failing is not, having a go and getting the wrong result is is fine, is what you have to do. It's what scientists do all the time. That's the only way really you get to better information. um and it's what artists do all the time as well. I mean, that's clear as well, that there's this expectation, if you're doing music or if you're writing something, it's going to be brilliant the first time, like all the things that you hear and see online. Whereas most artists chuck away half or
yeah.
more of what they make. So I think if we can sort of bring back failure in a peculiar sort of way, the right sort of way, then that, I don't know whether that is an aspect of what we're talking about.
Yes, I think that's absolutely true, and it's I like this as a sort of note to maybe to end on, because it goes back to the schooling system, which is another thing that I'm broadly speaking interested in, because I like to understand how I'm interested in the way people learn, and in how to keep this beautiful engagement that you see in young children alive throughout one's life. Such a shame that maybe you see then a pupil 7, 8 years later, and they look very bored with what they're doing, as opposed to what they used to be in the early years, so enthusiastic about learning anything. And I think the schooling system probably is getting this. The education system is getting this wrong. That it's suggesting, as you said, that failure is unacceptable in some way. Whereas actually, it's just basic stuff for learning. You can't learn anything if you don't get something wrong. It's obvious. And science is actually the falsifying things is vital. If you keep
Mm.
if you getting if you got certainty, you don't have anywhere to go.
Yeah.
It's certainly is the great enemy of any kind of intellectual progress. You just, if suddenly everything is stuck and there's no progress
Yeah.
occurring, you've got nowhere to go, right?
Yeah. Yeah.
Um, and maybe this is why science is sometimes perceived as less appealing than arts and humanities, at least in some students. Often, you feel like physics or biology or chemistry, or especially chemistry and physics and maybe maths as well. They're all about being right all the time and
Exactly.
having
Getting the right
certainty.
answer. Yeah.
Um, and this may be something unappealing to most pupils who feel repelled from the subject, and then they go somewhere else, which is such a shame, because I think part of the beauty of physics is that you get things wrong and you've got something to discover once to learn how to fix the mistake. Um,
Yeah, and I think it's generally sort of acknowledged by working scientists that the best are the most creative. They're not the ones that have just sort of churned out right things throughout their life. They're ones who have really had influential ideas
Yes.
that sometimes themselves might be wrong. I think that's the thing, or that might require, updating and refinement and so on. But the idea itself sowed a seed that was productive. That to me is the real way to judge a scientific theory. Not is it right, but was it productive?
Yes, that's absolutely true. Yeah. And if you look at these early papers on quantum theory, or even the early papers by Einstein about relativity, special relativity, and then general relativity, then you can see that these people actually change their mind throughout their lives about their own,
Yeah.
these very theories that they invented. They understood them differently across the years, and they were actually happy to say they were wrong initially. So there's an interesting. I think maybe at the time it was okay to actually say, "No, sorry, I was wrong, and, I thought different about this at the time, and it was a mistake." It should be normal to do it now, actually. It so yeah, in a way, I wish we could, reignite bring back some of these old-fashioned styles of communicating, of talking, and of teaching. And maybe we will, I don't know. But I guess a conversation like this would be already nice to it's nice that we're doing this, because I think, um, I like this free flowing conversation, because, it gives an insight to for people who are not maybe scientists, to into the kind of playful, discussion style that should be actually the bread and butter of physics. It's how ideas get created.
Well, I hope so. It's been great to have it in any case. We're probably used up our time, haven't we? But
Yeah, it was
it
fun. I
was
really
it
liked
was
it.
very nice. Yeah.
Thanks. Thank you for doing this. It was
Oh, my
fun.
pleasure. Thank you.
Yeah. And yeah, and thanks for all the stuff you're writing. I really enjoy it when I have time. I don't have a lot of time now on my hands, because but when I can read things, I do enjoy your things. They're cool. They're really cool.
Fantastic. Thank you so
Thank you.
much.